So,
Okay.
so as a very quick reminder, I'm working on seismothermomechanical models. And the speciality of these models of this version I'm working on, which differentiates them from the models that Maike is working with, is that unlike the already existing models here on the left, for example, a collision zone, which can only resolve time steps down to maybe a year. These models are built in a way that they can resolve millisecond time steps, but they are not finished. They are already working to a certain extent, but they are not finished. So my progress over the past months has mostly been improving on what already exists. So I will show you some of the things, the most important things I've done. And some of the problems I've faced over the past months to get a reference. The main scientific thing is that these models can produce earthquakes, but only one, and afterwards the plates don't relock and nothing more happens. Also, there are many instability issues. Many have to do with the boundary conditions. So these will come up again and again. One initial problem was that the first phase, where you run the model over a longer time to get an initial setup, took a long time. I did change that before Christmas. I fixed that, so now it's easier to make new model setups. And also many features of the old version were missing, and I reintroduced some of them. For example, just recently, the material output. So now you can see what's happening again. So this is the basic setup right now. It's just a subduction zone, not a collision zone yet. So you have a subducting slab and some wedge material here. One of the main bugs that I came across, which I wanted to show as an example of what I'm doing right now, is what I like to call the death spiral. So what you have right here is an earthquake. You have millisecond time steps, meter per second velocities. This is a bit difficult to see here, but the velocities are meters per second, and the overriding slab moves to the left and up, and the subducting slab, the overriding plate moves to the left and up, and the subducting slab moves to the right and down. So everything is fine. Nothing looks bad here, but the next time step, the model fails. And I looked into it, what's the reason? And it's some small detail in how the time steps are calculated. So this is the flow chart for a time step. The exact details of this are not important. What does matter is that when the movement equations, the Navier-Stokes equations, are solved, the they are solved iteratively. They are trying to minimize a certain error, and only when that error crosses below a threshold is the next time step. Will the model proceed to the next time step? And within that convergence, there is a certain condition that if the errors ever increase over this iteration, over trying to decrease the error, it restarts with half the time step, which should ensure convergence, but sometimes it also leads to problems like this, where you see first iteration, second iteration, errors increase, restart. And this continues, and in the end, it just crashes. And this was a very common error, one that even in previous iterations of the model before I worked on it came up often. And the solution is relax the reset condition. And this has worked. And because that worked, I can now show you the results of this model, one of the models I ran with slightly changed parameters. So this will be an earthquake, the model generated. So what you see here is the strain rate, and this is the subduction zone. These are isotherms. So between this and this, between these two isotherms, is the rate weakening zone of this subduction zone here. And yeah, I'll just show you. You can see now there are millisecond time steps, and there's movement across the plate interface, and also seismic waves are being generated from this point onward. You can also see here the fault, the earthquake progressing up dip, and then coming to an arrest once it reaches this transition zone here at the end of the rate weakening zone. Maybe someone already noticed when I showed this figure here earlier, but there's a gap here. This is air. The white is air. So there's just a gap here at a very steep slope. And for a long time, for example, for the model I just showed you, this didn't provide any issues. But when trying to, for example, reduce the fluid pressure so that the material is stronger and the plates will relock again, hopefully, after the earthquake, this happens where here, this is the entire model. Here you can see an earthquake, just as I showed before in the megathrust. But here there's also very fast movement at this gap, and it's a problem. It leads to it results in crashes of the model. You can also see here in the viscosity, this blue wedge going in here is just the air. Also some issues at the right boundary conditions. So these are things I'm working on, I'm trying to fix. And this is currently ongoing. And the main reason for all of this, again, this is the main point. I want this model to be able to generate more than a single earthquake. And for that, I'm changing parameters. But the second I change parameters, everything breaks. There is some new error. It's truly impressive how many different errors this model can produce because of the complexity of what is being simulated. The viscoelastoplastic rheology coupled with temperature just leads to many different ways in which it can fail. And one other step we wanted to take is just to increase the model depth so you can let it run for a bit longer so the subduction zone is more mature. And yeah, so I'm currently working on that. And this is a model, this is a figure which I just generated. So this is right now the current state of one of the models. And here, maybe you can see the gap is filled with another material. So this is a promising attempt. There have been a couple of attempts which have failed, but yeah, this is the type of work I'm doing right now, and hopefully it will lead to the behavior we want to see, which is multiple earthquakes in a sequence.
Okay, thank you, Alexander. So are you working like are you getting some help on this, or what do you work actually?
I mean, Ilona is of course helping me.
Okay, good.
But much of this, to be honest, I've just done step by step myself, because the good thing with the already existing code is the output is quite detailed. So if you just look at the log files and the like, you can usually figure out what the problem is and then go from there, try new things. So this is what I'm mainly doing, just trying things, seeing what happens, and choosing new approaches from there.
All right. So it's a trial and error type of.
Yes. So I'm currently at over 60 different models, which I have started, many of them in the last month, just because many of them fail. But over time, there always come these improvements, which then lead to new errors and hopefully eventually usable results.
And the absence of relocking is due to some specific reason, do you know?
And I assume it's just that it's too weak. So there is stable sliding. There's just, yeah. The problem is this first phase behaves a bit differently from the rate and state friction phase in which the earthquakes are supposed to occur. So the initial loading, which leads to the first earthquake, is not really, it's not the same as what's supposed to happen afterwards. So the fact that one earthquake can happen is not surprising in this sense.
So you're trying to first get some permanent type of stress field and then run the simulation from there. Is that right?
It just begins from the initial setup. So the stress field is just.
Yeah, but I mean the first training period, or spin up, as I call it. So you're trying to load the model first. Is that right?
Yeah. So there's this first phase, this long-term phase, where you can see here, for example, this has been 500,000 years, and it's will run for another 1,000,000 years until this setup is reached, where there's already some loading that has occurred in this phase, where yeah, the plastic failure condition is a bit different.
Okay. Okay. Any questions? Anybody? So at the moment you're training yourself on a subduction context, and then I mean the idea is to work on to simulate, I mean, a specific target. Sorry, I forgot. You probably
So in the beginning, it's just a generic model. At the last stage, we're planning to move to a specific model with more constrained parameters. But right now, it's generic to get the method to work better. And that's why we also have decided to, for now, stay with the subduction setup, because if the subduction doesn't properly work, the collision will definitely not work properly.
Right. Okay. Goody. Okay. Questions, anybody? Nope. Okay, so we can move on then. Thanks, Alexander. So Rachel, that's your turn.
Yep. Okay. Can you see the presentation? Okay.
Yep.
Just 1 second. So yes, I'm working on project 8. Just the title is Integrating Physics-Based Earthquake Rupture Models in Seismic Hazard Assessment. I'm just going to quickly remind you of the main goals of the general PhD and what we have settled on as the first project, and then give you an update on what I've done so far. So the motivation of the project is that a classic seismic hazard assessment is limited by the finite amount of empirical data. So this is where simulated data from physics-based models can help. And there are sort of 3 main processes that will go on throughout the PhD, which include developing 3D dynamic earthquake rupture scenarios, and from these simulate ground motions to then compute seismic hazard. And from the 3 main chapters that we have decided on, I have started working on the first one, which is do physics-based rupture models capture ground motion variability, with insights from last year's event in Turkey. So first of all, this event was an earthquake doublet, with the first event nucleating on this display fault over here, and then branching on to the East Anatolian fault, producing a 7.8 magnitude event. And then 9 hours later, there was the second event, which occurred on this fault. And this was a 7.7 magnitude event. So there's a lot of, there have been dynamic rupture models already produced by, even from my research team, such as from papers Gia et al. And Gabriel et al. And these have provided explanations on different puzzling features from these events. And they have also reproduced quite well at first order geodetic and seismic data. So the next question is to look at the ground motion, and I started looking at the pulse properties. So on comparing observational data and synthetic data, the synthetics don't really seem to show the variability observed. So what we're looking at here, the circle sizes represent the amplitude of the pulse, and the colors represent the period of the pulse. So since this variability doesn't really seem to be observed, it implies that the models are a bit too smooth. So what can we do to capture this ground motion variability? We're considering the structural heterogeneities, so different velocity models. And we're also considering on-fault heterogeneities, including fault roughness, different fracture energy by varying DC, pre-stress, and super shear. So from a study on the Amatrice earthquake, it was seen that on-fault heterogeneities allow the reproduction of ground motion metrics up to 5 Hertz. And from a recently published paper, they really saw an increase in the strong shaking when compared to subshear scenarios, which leads to the idea of really including varying subshear, especially since they observed different patches of super shear along the fault during the event. And for the time being, I have started to focus on the fault roughness. So someone from the team has already actually simulated a rough fault simulation. So I just went ahead and looked at the ground motion from the simulation and compared it with the observed and the smooth simulation. So the black is the observational data, the pink is the smooth, and the blue is the rough fault simulation, where overall the timing and amplitude of the ground motions do seem to be well reproduced at first order. And in fact, if you look closely, the timing of the rough simulation seemed to be more similar to that observed, with a smaller amplitude than the smooth. But overall, both don't really seem to reproduce the high frequencies that we can see in the observed data. So then I took a look at that without any filtering applied, and there still don't seem to be these high frequencies. So I took a look at the velocity spectra of the smooth and rough and observed data from stations that are off the fault. So this is from the stations that I have that are farthest from the fault. And by looking at the fall off from the spectra, you can see what frequencies are actually resolved. So for the smooth simulations, we can see that the fall off is occurring at around 1.5 Hertz, and for the rough at around 2 Hertz. And this changes as we approach the fault. When we're a bit closer, the rough seems to keep on following that's observed, the same trend, and the smooth seems to fall off at around 5 Hertz. And even closer, this seems to occur at around 7 Hertz, even for other stations at close to the fault. And then when we start moving back out, we move back to the 1.5 Hertz for the smooth and 2 Hertz for the rough. So what's important to note is that a rough fault setup makes use of much higher resolution and a much larger mesh and many more resources. So it's overall a much more expensive simulation to carry out. But having such high resolution doesn't actually guarantee the generation of the high frequencies that you observe. And in fact, that's why a lot of studies tend to not use physics-based rupture models. So we really wanted to see if these expensive simulations are actually worth in the end. So from this, we can more or less confirm that a lot more high frequencies are actually generated, especially at the source. So then I wanted to look a bit closer at those near the fault. And so basically what I did is look at the whole spectra. It's the same data that we saw before, just looking at the whole entire thing. And looking at the rough simulation, we can see that it more or less follows the same trend that the observed data has. And there's this end bit, which I wasn't entirely sure how to interpret, whether it can actually be interpreted as a fall off. So stating that the rough simulation is resolving frequencies up to 25 Hertz, more or less, or if it is just the end of the spectra, because in fact we are seeing frequencies up to about 50 Hertz, which makes sense because the sampling frequency was 100 Hertz. So yes, I would like to continue analyzing these spectra and try better understand them. In fact, I would like to further confirm that no other processing was done to the data before I got my hands on it. And then I would also like to check out the mesh, because we make use of a statistically unstructured mesh in these simulations, which means that the element size and resolution are fixed at certain points. In fact, we could see that as we approached the fault, the resolution, the highest frequency that was resolved, started increasing. So I would like to figure out where exactly the resolution is fixed. And I've also more or less started the beginning phase of trying to vary DC, where we're actually going to follow an approach taken by Ida and Oachi, where they applied circular patch asperities. So basically, to have a complete variation of your DC size, you define different orders of patches on different scales. And this is a little representation from the paper of how they do this. And you end up with this final picture. And this is basically, we have a colleague who did a similar study and passed on the scripts, and I just wanted to try represent what it would look like. So that's it from me.
Thanks, Rachel. Okay, so I have several questions, but maybe somebody else can ask. Yeah, Ilona, go ahead.
Yes, very nice work, Rachel. So in the first few slides you showed, I was a bit puzzled because it seemed as if the smoother fault actually had higher frequencies there. So I saw it already based on this slide indeed, and then on the next one as well. And it only holds obviously if you're very far from the fault. So once you went clearer to the source, this disappeared. But do you have any idea why that could be?
I'm not entirely sure. From what I've understood, it's that just because you are including roughness doesn't necessarily mean that it is the right approach. And we were also discussing that maybe it's a way in which the roughness is implemented, that it's sort of not completely considering it in a way, in simple terms. So it's something that comes down to the details of the code, which I haven't really explored yet, but that is a thought.
Okay.
Yeah, actually, yeah, go ahead, Ilona. Yeah.
No, yeah, just continue on this. I have a follow-up question, but
Yeah.
yeah. So why would it then change with distance? Because presumably you have the same medium in there that has also the same attenuation.
Well,
your later slides that are closer to the fault, the rough fault seems to do what we expect it to do.
yeah.
So why this difference with distance to the fault? What changes in the medium? How can you explain that?
In fact, actually, so these are actually all on fault, exactly on the fault, because we're looking at the pulse. And when we looked at the spectra with the data exactly on the fault, you don't really, it's very difficult to try and understand what we're looking at, just looking at the spectra. And that makes sense because technically the principle is applied to off-fault data. At this point, I interpret the fact that we resolve higher frequencies closer to the fault because the mesh is a much higher resolution as you approach the fault.
Ah, so in the two cases, the mesh size is also variable. Ah, okay. Yes, that will then probably be the explanation for the distance that is there. Okay. Okay, thank you.
Okay, thanks, Ilona. Actually, Rachel, how do you didn't run the simulations, but can you say a little bit more about, this roughness, what it is actually within the code? I mean, what is it? Does it represent? Is that the geometrical roughness, or is that yeah?
Yeah, it's the geometrical roughness.
Okay, so how is it simulated? Is that like a fractal surface, or?
It should be a fractal geometric roughness that's laid on as another layer on top. So you have the geometry of the fault, and then layered on top is the layer of the geometrical roughness.
Okay. Because I mean, if you lack, you know, high frequencies, and the first thing you know that spring to mind is that, you know, you just haven't simulated enough roughness on your fault, you know, basically. So maybe just to increase the roughness and check if you can, you know, simulate your high frequencies might be, you know, worth checking.
Mm-hmm. True.
So at some stage you will get your hands on the simulation yourself, yeah?
Yes, it should be this week where I'm going to start trying out the DC simulations.
Right.
Even just running something very small for a couple of seconds just to see that everything is working and whatnot.
Good. Good luck.
Yes, have fun.
Okay, thanks a lot, Rachel. Any other question, maybe? I don't know.
Or anybody who has a nice update they want to share with the group.
Yeah. Yeah, if some of you have, you know, came across a new discovery, you know, you just need to test. Don't wait for your turn.
Yes.
It's a bit early in a PhD now, but okay.
No, it's nice to see that both Alexander and Rachel already have cool results to look at. So
Yeah. Indeed. Good. So thanks. So we can move on to the lecture itself. So Vitor, yep, you're here. Good. So basically that's you have the scene for you. So again, everybody don't hesitate to interrupt Vitor if you have questions. I mean, that's the goal. That's you know, or a tutorial or no, that's proper lecture, but still, I mean, don't hesitate. You know, that makes for a more lively discussion in the end. So you can go ahead, Vitor. Thanks.
Can you hear me okay?
Yep, we do.
Yeah.
Okay, very good. Yeah, you can hesitate a little bit, you know, about interrupting, but I think that's okay. Thank you very much, David. David, just remind me, how much time do I have?
Well, I mean, it's typically 1 hour is good, so you know everybody can stay awake for an hour and
Okay, let's yeah.
You know, more than an
Yeah.
hour, you know, you're starting to, you know, go into, you know, the limit zone of some of us.
I totally understand the death by PowerPoint. Yeah, very good. Yeah. So thank you very much, David. And first of all, congratulations to the previous students that were presenting, despite the fact that I will explain in a second, you know, what's my you know, area of expertise. But it was relatively simple for me to follow, let's say, the main you know, concept. So it's very nice to see that, you know, so early in the game, but it's still already very nice to see very good research. The reason when I was discussing also with David about you know, when GEM can provide some lectures, you know, some presentations, I wanted to present, you know, like as soon as possible at the beginning of this course, because I just wanted for the students also to understand, you know, why are we improving some of these Azure modeling techniques, you know, this way of, you know, either triggering the ruptures or doing better modeling of the ground shaking, of the uncertainty in the seismic hazards in the ground motion. I feel like it's so important for the students to see this science is nothing that it's abstract. It's not just a plot. It's not just a map. You know, there's a purpose for the students to be improving this Azure modeling techniques, right? And I think typically it comes a little bit down the line. I've been in many projects that basically, I would say that 90% of the project is about Azure modeling or seismology or tectonics. And then the final part of the project is actually trying to understand, okay, but does it make a difference, this new methodology that I just developed? Am I going to design buildings differently? Is the seismic zonations for the various countries now going to be different? If I want to use the seismic hazard model for risk reduction or disaster risk reduction, disaster risk management, is that going to make a difference? And I think that's an extremely important question because a lot of times these methodologies have an increased complexity in terms of computational demand, in terms of the data that is required to develop these models. And I can say that in a lot of the cases, when it comes to the hazard, the answer is yes. You know, when it comes to the hazard changes so much the earthquake risk that actually these improved methodologies, they do change the risk considerably, and they should be considered. But I think it's quite important for us to really justify, you know, this increase, for example, on the computational demand or in the requirements for the input data. So my name is Vitor Silva. I'm the head of risk engineering at the Global Earthquake Model. My other colleague, Marco Pagani, is also one of the participants on this project, on this ITF. I'm supervising a student, Julian Montejo, who is also on the call. And we also have another student, Farouk, that is also here on the call and is working with Marco Pagani. So at the Global Earthquake Model, I lead the team that deals with the assessment of the impact from earthquakes. And that's exactly what I will be talking a little bit on this presentation. So it's all the way from the rupture to the risk. And my goal, again, as I was mentioning previously when I talked to David about trying to present sooner rather than later, was exactly to try just to provide like an overview, high level of this entire process of digesting hazard information and producing data that is used, for example, for institutions like the European Union, the World Bank, different countries, the Italian government, for risk reduction. So this way you would have like a good picture of the entire process end to end. So just to understand what do I mean, you know, by earthquake risk assessment. So the hazard part.
Sorry to interrupt you. You're not in
Yes.
full screen mode, so
I'm not in full screen mode.
which
Okay,
is
thank
okay,
you.
but okay, that's better. All right, thanks.
That's definitely better. Yes, thank you so much, David. I'm surprised that none of the students told me anything about it. Not even my students. Okay, thank you. There'll be consequences. So here on the earthquake risk assessment, so there are three main components, as I was mentioning previously. It's the hazard, which is basically just the likelihood of ground shaking in a given location. This is something that at least 2 or 3 of the students in this ITN are going to be calculating. We have also the exposure, which is basically just the location of the buildings, of the people, of infrastructure, of trees, of people. And then finally, we also have the vulnerability, which is the connection between the hazard and the exposure. And this is typically the definition that is used by the Global Facility for Disaster Risk Reduction. It's not my favorite definition, but it's one that I see in a lot of publications. So before we actually get into the complications and the complexities of these 3 components, I just wanted to give you some examples, or some of my favorite examples, when it comes to using some of this data for disaster risk reduction. An example that I like very much to mention is what happened in Italy many years ago. So this was a presentation by Professor Mauro Dolci at the World Conference in 2012 in Italy. And it was basically showing how after the L'Aquila earthquake, the Italian government invested, I think it was 1 billion euros in risk reduction. And I remember telling Mauro that, my God, 1 billion euros, that's a lot. And then he told me that the civil protection estimated that 1 billion euros was only 1% of what was necessary to properly reduce earthquake risk in Italy, which was very impressive to me. But obviously they needed like a criteria to distribute the funds across Italy. So doing probabilistic risk assessment is a way for us to do this. So basically they estimated what were the expected losses for the different provinces of Italy. And then the funds were distributed proportional to the earthquake risk. So unsurprisingly, more funds were given to the southern regions of Italy and not so much to the northern regions where the seismic hazard is lower. I also had the opportunity to be involved in many projects with the World Bank. And before this call, I was actually in more calls about these initiatives from the World Bank. It's quite often the case that basically they need to do seismic risk assessment and seismic hazard assessment for different cities in different parts of the world, for countries, considering different challenges, considering the risk today, but also the expected risk in 50 years. And then they use this information to basically provide funding to the student, well, sometimes also to the students, that's true, but in this case for countries to reduce earthquake risk. I will show some examples in a second for what was done for Turkey and for some countries in Africa. But this is typically an exercise that it just brings a lot of responsibility, because it's no longer just like a publication, a paper, or just a study. You feel the pressure that people will make important decisions based on some of the information that you're going to produce. The reason I included this example here, it's precisely because within this ITN, a lot of you are going to be developing high detailed, very advanced methodologies for seismic hazard assessment, which are very, very important when we think about earthquake risk at the city level. And this is, for example, what you see here on the right, in terms of the risk for the various cities. This was a project for Eastern Europe. But this was quite important because I lost count of the number of seismic risk analysis that I see for cities, that basically people just use national models, and then the results look strange, let's say. Let me use the word strange for some of these cities. So I hope that some of the outcomes from this ITN are also going to allow us to have better seismic hazard estimations at the urban level. Something that is also quite important is insurance. A lot of these large insurance companies, reinsurance companies, cat modeling companies, they do fund a lot of research. The Global Earthquake Model, the foundation that I work for, a lot of the funds come from the industry, the insurance industry. And it's very important because in a lot of countries, for example, you might remember the earthquake that happened in New Zealand. If there's a good insurance coverage, this typically helps reducing the financial gap. And it accelerates the recovery of the countries. In other places, that just doesn't exist. I can tell you that, for example, before 2002, Turkey didn't have a large catastrophe insurance pool. So basically it was constantly the government that needed to have the financial burden of helping the population in the recovery process. Then they created their insurance pool. Now they have, it's called ASK. And basically they reduce the financial gap. So every time that something happens, like now happened with the earthquake in Turkey, in theory, there are funds to help with the recovery. And for example, in this map here, just showing that insurance gap, the quality of the figure is terrible. I apologize for that. But basically this is almost no insurance, okay, all the way to having a better coverage law, okay? So I can see that in the Western world, there's a good insurance coverage. And then in the less developing world, we can see that there's almost no insurance coverage. I just wanted to mention here some interesting examples. For example, a lot of times the World Bank, the European Union, USAID from the United States, JICA from Japan, they just give this multi-million grants for the countries to reduce earthquake risk or natural hazards risk. And I just want to highlight from this example and also this example that a lot of times this funding, it's not for next year. It's basically the strategy for the countries or for the region for the next 10 years or 20 years. And you will see towards the end of the presentation why it's so important not to consider just today's risk, but also what we expect the earthquake risk to be in the future. And the final two examples that I wanted to show you was we developed a seismic risk model. We estimated economic losses, damaged buildings, fatalities for Turkey before the earthquake happened. So this was a few months before the earthquake happened. And this was a project with the World Bank. Then with the results that we produced from this project, they went to the Turkish government. They said, this is your risk. I really think you should improve the resilience of your buildings. In this case, they also wanted to improve the energy efficiency of the buildings. And first, the World Bank provided a loan of $265 million. After we finished the project, this was during the project, we actually highlighted that the risk for Turkey was much bigger than what was initially thought. And then the World Bank provided another 512 million, okay, to Turkey. This time it was not only for earthquakes, it was for earthquakes, but also floods. So that's also why the value is much larger. But we can see here that the type of work that you're doing, you know, this seismic risk analysis, they can basically be like the tool that it's also necessary to raise funds for risk reduction. All of this stuff that I'm showing here for Turkey was before the earthquake in February last year. In the meantime, I talked with some of my colleagues that work on this project on the World Bank side, and some of these funds have obviously been now diverted for reconstruction of the southern part of Turkey that was affected by the earthquake. But a couple of days ago, I received another message saying that because people saw what happened in the south of Turkey, now they are asking for additional risk analysis specifically for Istanbul, okay, because they just fear that a lot of the buildings in Istanbul might be also as fragile as the ones in the south. So again, urban risk analysis require detailed hazard assessment, like, for example, the ones that were being showed previously. So I just want to mention that I think I started working on this, 15 years ago, and there was obviously some good information about seismic hazard and exposure. There's been some hazard and risk analysis since the 70s, since the 60s, in fact. But since then, obviously, there's been like so much research, so many papers and publications and PhDs all over the world, and different departments and research institutions have been created. We know more about earthquake hazard and risk than ever before, but the economic losses and the number of disasters keep increasing. So we know more, and our reward from knowing more is that we keep having more and more disasters. And I will discuss a little bit why do we have more disasters and more economic losses and more human losses if we should be better than we were, for example, in the 60s and 70s when some of these studies started. And because of recognizing that the risk keeps increasing, there's this framework that was developed, it was proposed in 2015. It was in Sendai in Japan. And something that was quite important about this framework was that 187 came to Sendai, or representatives of 187 countries came to Sendai, to Japan. They did this in Japan because, as you might remember, in 2010 and 11, there were the earthquakes in Japan, right? The Tohoku earthquake. And so they decided to do this meeting, and then all the countries agreed we need to reduce risk. Okay, and they established some metrics. They said, let's meet again in 2030. So basically, it's going to be in 6 years. Let's meet again in 2030, and then let's see if the measures we're going to take in the next 15 years allow us to reduce the risk or not. Okay, and the first priority is exactly understand risk. This is what's written on this agreement that was signed by 187 countries. Also, something that was quite unique about this framework, because there were other frameworks before, but this one was that they said, let's actually quantify the risk. Let's not just say, oh, I want to reduce the risk. Well, let's put numbers on it. Okay, let's see how much can we reduce the risk, for example, per 100,000 inhabitants, as a fraction of the GDP, as a fraction of the capital stock. And also, let's try to make sure that we're going to reduce the risk, but let's try to be sustainable in this process. And I will talk a little bit more about that. So what is happening in some of the countries, for example, in countries that are growing a lot, like, for example, some countries in Latin America and Southeast Asia, what happens is that we have this present risk. And in 2015, when a lot of this stuff was being discussed, we know that population keeps increasing in a lot of these countries. We have more buildings, we have more people. We have buildings that unfortunately keep being more fragile, right? We have more people building close to active faults, building in places where we can have liquefaction and landslides, building in places where we know can be affected by tsunamis. So in fairness, the risk is increasing. Even if you neglect that some of the buildings, are not maintained and the fragility might increase, just the fact that we have more people, we could say that the risk is increasing because we have more people that might die or might be injured due to earthquakes. So let's say now that this is my target. I have to reduce, earthquake risk. I have to reduce disaster risk. And this is my target specified by the Sendai framework for disaster risk reduction. What happens is that if you do not take into account how much the risk is expected to increase, you could say, well, from now on, I'm going to always build my buildings according to the most modern design regulations. That's it. That's my only risk mitigation. Okay, but that might not be sufficient to reduce your risk, because the future buildings are going to be code compliant. But what about all the buildings that exist now in the country? What about all the buildings that are being modified, maybe not according to the design regulations? What about all the informal construction? When we visit countries, we've been in places, for example, in Nepal, in Kyrgyzstan, in Ethiopia, in Peru, where they take us to certain places and they show us, you can see that basically there's very recent construction, but there's no way that people follow design regulations. For example, also something that happened in the south of Turkey was not that there's no design regulations. Of course, the design codes in Turkey are very good. We check them. It's just that in a lot of places, those regulations were being used to design the buildings, but then what was being built on the site was different. So it is important to take into account the future risk and also design different mitigation measures to make sure that, once we get to 2050 or 2030 or whatever time point in the future, the risk is going to be below our threshold. We did exactly this for Turkey. Okay, we did this exercise using real data, okay, for Turkey, and I will show at the end of the presentation. But before we go there, let me just tell you why earthquake risk is increasing. And let's assume for a second that the risk is basically the area that you see in this triangle here, this present risk triangle. As I mentioned previously, if you just focus here on the right, on the exposure, we keep having population that is increasing, right? Even in Europe, okay, despite the fact that some of the population in some of the countries might be decreasing, we have migration, right? We have people coming from different countries. So just migration alone is increasing the population in some of the countries in Europe. And then if you imagine some countries, for example, in Africa, I think I have some slides about Africa. For places like Nigeria and Tanzania, in the next 30 years, the population is expected to almost double. In cities like Cairo in Egypt, the population is expected to almost double. So you can imagine that just this side of the triangle is increasing quite a lot. On the vulnerability side, we have informal construction. As I mentioned previously, we have unplanned urban expansion. We also have accumulation of damage. Okay, so there's an earthquake, there's another earthquake, there's a cyclone, there's a wildfire, and there's accumulation of damage on the building. So the vulnerability could also be increasing. And then here on the hazard, well, you could tell me, well, is the seismic hazard increasing? This is a question for the students, not for the lecturers and not for David. Question for you guys. Do you think the seismic hazard might be increasing? I'm going to pick a random person. So Gerard, do you think the seismic hazard is increasing? Might increase in the future? I cannot hear you, and I don't know if that's a trick. So you don't.
You asked me. I didn't
Yes.
hear you. Yes, I think that the hazard probably is not going to increase, but the methodologies are gonna change in all time probably. So the hazard probably is not going to be different, but we are going to have a best assessment of that.
Okay. Yes, but the physical phenomena, I agree that, seismic activity is not expected to increase, right? I had many discussions with many people around the world about this. And this is my opinion, seismic activity is not going to increase, but I can tell you that I had some heated discussions with some people from specific parts of the world where they really disagree with me. Okay, in some places they had some points, because they were talking about, what about all these places where basically now we have all this ice and the ice is melting and there's sea level rise, so now we have different saturations of the soils in different parts of the world, which might cause earthquakes to happen with a higher likelihood. Okay, maybe in the very, very long term we might have slight changes on the seismic activity. But something that we have to take into account is that seismic hazard is not just ground shaking. Okay, we also need to take into account secondary hazards, like, for example, liquefaction, landslides, and tsunami. Okay, and there's now very interesting research about how liquefaction is increasing because of the sea level rise. Okay, and I will talk a little bit more about this. One of my students is also studying there. And also how landslides might increase, the likelihood of landslides, because of the different patterns in precipitation. In some parts of the world now we have extreme precipitation, and then if an earthquake happened while those soils are very saturated, there could also be a chance of having a higher likelihood of having landslides.
So just a quick question: what about
yes,
human-induced activity, like earthquakes? So
very good point.
In the US,
Yeah.
it's clearly an important, subject. I guess the hazard is quite small still, but
Yeah.
expected to grow with time.
Yes, yes. So when I was having this heated discussion with my friend, she was from Croatia. I think she was almost losing the battle, and then she told me, "What about induced seismicity?" You know, and she has a good point. You know, there's induced seismicity, for example, in UK, in the Netherlands, and Oklahoma. You know, in the United States, the events are actually relatively high. There's also been some events due to collapse of mines, you know, in some specific parts of the world, in China, in Poland. So yes, we could also have added seismicity or added seismic hazard because of induced seismicity. Induced seismicity, it's a massive world of research that exists behind this, with many different groups acting on it. I actually think the gas field in the Netherlands is going to be closed because of that, which I was very much against that. But it's a very good point that we also have anthropogenic reasons that might be increasing the seismic hazard in specific parts of the world. So what I wanted just to go now with you, just over these three big components, you know, seismic hazard, exposure, and vulnerability. I will spend less time on seismic hazard, of course, you know, since this is something that you're going to be studying in a lot of detail. But I wanted to talk a little bit about exposure, vulnerability, and then show you some examples about risk. I think it's going to be quite important, for example, as you students going to conferences, you know, you will be talking with people, seismologists, hazard modelers, but eventually also earthquake engineers and risk managers. And I think it's quite important that the students, even if you're not an expert in seismic risk, you should be able to speak the same language, okay? You should be able to entertain a conversation with people that will be digesting a lot of the information, a lot of the models, a lot of the data sets that you might produce. With the seismic hazard, at least from the risk perspective, usually these are the questions that we're trying to address. You know, where should I expect earthquakes? What is their likelihood? What is the expected ground shaking, as we've seen, for example, on the previous presentation? And more, because of some climate change effects, secondary hazards are becoming extremely important. From a risk perspective, usually we have like two big schools of thought, okay? Either you consider just a single event. Okay? For example, I'm just showing here the median ground shaking using a given ground motion model, considering the characteristics of the Armenia earthquake in 1999 in Colombia, okay, just a single event. Or we consider all the possible events that happen in the future with the associated rate of occurrence, okay? This is, for example, typically what we do on design regulations, where we need to take into account, you know, the seismic hazard. There are benefits and disadvantages in both approaches. I can tell you that the approach on the left, you know, doing earthquake scenarios, it's easy to understand by a non-technical audience, like a civil protection, or when we talk with people from, you know, urban planners, people from the city halls, or the general public. You know, if you tell them, oh, I'm considering all the possible events that happen in the future, they're like, you don't know that, you know. But if you show like specific events, saying, I'm giving you the consequences from an event, historical event that happened in this country. If this event happens again, this is the consequences that you should expect. Typically people, oh, I can understand that, you know, because if it happened in the past, it might happen again in the future. So I can deal with that. If you might even do some hypothetical events that never happen, but because you have very good information about the faults, you know, how much, what is the maximum magnitude that this fault might generate, you can say, I don't have a good historical record of what might happen in this fault, but this is an hypothetical scenario. And this is something that is very powerful when it's communicating with people from an audience that might be a little bit less technical. I, on the other hand, because I want to believe that I understand a little bit more, prefer much more the probabilistic approach, okay? Because for me, I think taking decisions considering just a couple of events, it's dangerous, because you might design your entire risk assessment, risk mitigation based on a couple of scenarios, and then in the future, those events don't happen. Other events happen, okay? So, and you didn't take those into account. So on a lot of the work that I do with my students and on these projects and with my risk team, we tend to follow more the probabilistic hazard approach, in which we try to consider all the possible events that happen in the future, and we use probabilistic metrics. So for your activities, I just want to mention that as part of the global earthquake model, my colleague, Marco Pagani, he has basically compiled this mosaic of seismic hazard models around the world. Okay, some of them are regional models, some of them are national models, some of them are a combination. And by doing that, he has also developed this global seismic hazard map. Okay, this is basically a map for peak ground acceleration in Gs in terms of PGA. Okay, on rock, there's also the same map, but then for VF30 derived from topography. But this is basically information that, you know, if it's useful for your risks for your studies, your PhD studies, I just want to mention that all these models are available for your activities, even if you just want to do some comparisons. But this is it in terms of the seismic hazard component. I use and abuse of a lot of the models that my colleague Marco produces, this probabilistic seismic hazard model that he either generates or compiles from the literature. We do a lot of impact analysis from these seismic hazard models, or sometimes we also do earthquake scenarios, historical, hypothetical events that we basically just extract from the earthquake rupture forecast from some of these models. And with that, now I want to move to something different. Exposure.
Oh, sorry, Vitor, just a quick question on your map. I mean, there's no probability there anymore. So what is that? Is that the maximum acceleration that you can get over this time period? Is that right?
There is still a probability. Okay.
Yeah,
this is for the 475-year return period, which means that this is the ground shaking that is expected to be exceeded with a probability of 10% in 50 years. Okay. It is a bit strange, you know, to use this 10% in 50 years. You know, this is something that there's literally like a paper that shows that there's no like reasoning, like a solid reasoning behind this. It's just that a lot of times, you know, for buildings, I'm a civil engineer. For buildings, we design typically for 50 years, right? Buildings are supposed to survive 50 years, unless it's a critical building, and then we consider like a longer time horizon. And then the 10% was basically something that was decided a long time ago. But, you know, if the building is going to be, let's say, designed for it's supposed to survive 50 years. Let's make sure we're going to design for a probability that has at least a 10% probability of being exceeded in 50 years. In other parts of the world, this is not the level of frequency that is used. Okay, in other parts of the world, it's actually 2% in 50 years. Okay, so but this is something that the 10% in 50 years or the 475 years, it's just something that is very common and very useful to compare the seismic hazard between different countries.
Okay.
Just something quickly, because David, you raise a very important point. You know, there's other schools of thought in different parts of the world where they do not necessarily believe like in this 10% in 50 years. So they go for the maximum, you know, ground shaking. You know, there's this deterministic approach going for the maximum ground shaking that can be generated in different parts. This is a valid approach, of course, but sometimes this might lead to extremely high ground shaking. It just might become impractical to design buildings, like all the buildings, the entire building stock of a country, for such a level, a high level of ground shaking. So just moving here to exposure. So questions we're trying to address on the exposure side. So typically, okay, so typically, what we want to address is what are the buildings, how is the building stock, how many occupants are inside of the buildings, and how much do the buildings cost, okay? And this is the type of questions we're trying to address. Stuff related to the exposure, it's strange, because you could tell me, well, exposure should be easy because I can see the buildings. I can go there and I can touch the buildings, right? It should be more complicated when it comes, for example, to the seismic hazard, because you know, I might not see the earthquakes. You know, what I have is earthquake catalogs and information about faults, and I can do some trenching, but it should be easier to deal with buildings. But unfortunately, this is often not the case. You know, I can tell you that I work with many countries where I even asked how much was the population, and they told me they were not sure. You know, in Papua New Guinea, they said that in a lot of parts of the country, they're not sure, for example, of how many people exist. And of course, if we want to do risk analysis for small cities, this is actually a photo of one of my students. Okay, this is Pavia, you know, the image that you see here on the background. If you want to do like a small risk assessment. You can even go building by building. You can take photos. There's many apps now. Many years ago, there was or maybe only one or two. Now there's many apps where basically you can just take photos of buildings, collect the latitude, the longitude, the attributes of the building. And I can tell you, this was during the risk course. I just divided, I had 40 students. I divided the students into different groups. I think it was groups of 3 people. And in one afternoon, they went into the city. We divided the city in different regions. In one afternoon, the students collected information from buildings in this area, in this area, in this area. They collected information from 1,500 buildings. We then collected all the data. We compiled everything into the same exposure model. And then they ran risk analysis for the city of Pavia. This is possible if you have an army of students, in this case, 40 students. Most of them were civil engineers, maybe less than that. But again, people with some technical background, and there was only 1,500 buildings. Okay, and I think if I asked my students for more than 1,500 buildings, I would probably drop the class. Okay, so this was the maximum that I could push them. If we want to do something larger than that, okay, just to show here the results, this is all the buildings that were collected, 1,500 buildings. This is the center of Pavia. It's very beautiful. I really recommend you to visit. If it was something a little bit bigger, I think it would have been a little bit more complicated. We've done this in Portugal for the one small part of the city of Lisbon. It was 3,000 buildings. And I also managed to get the students to collect information building by building, but I had to pay the students to do that. In some cases, it is possible for us to collect information building by building. What is the type of information that is collected? Well, for example, the material of construction, the number of stories, when the building was built, the type of roof, if it's a residential, a commercial, and industrial building. All these factors, as I will talk in this presentation, influence the likelihood of the building to suffer damage or not. Okay. In some other places, for example, this was a very interesting project in Zagreb, in Croatia. It was fantastic because basically the City Hall of Zagreb, and then also the colleagues from the University of Zagreb, they already had a model, a 3D model of the entire city of Zagreb. Okay, and then they even went, building by building again, but this was a multi-year project. They collected information building by building. So in some cases, you might have these cadastral data sets, which have very good information. Okay. There's also some good information from this open initiatives, like, for example, OpenStreetMap. This is OpenStreetMap for Kathmandu, Nepal. The city has been extremely well cataloged because of the earthquake that happened in Gorkha. Okay. And then there's also other initiatives where, again, they've been building, 3D versions of the cities. Like, for example, I think this is New York, if I'm not mistaken, Manhattan. And in these cases, we do have some good information about the building stock. Okay. However, I will just mention that what typically we have, it's not the information that I need as a structural engineer. I need to understand, the type of material, the number of stories, when was the building built? Is it an irregular building? Is the building well maintained? And a lot of times in these initiatives, they just do, the 3D models of the cities. Okay. And by the way, just out of curiosity, I had some meetings, with people like, for example, from Google, from Facebook, that were building these data sets. And I asked them specifically, like, what would it take, for you to collect information about if it's a steel building, a concrete, a masonry building? They told me that it was very unlikely that they were going to collect that information, because one of the reasons they build these models is because of computer games. Okay, they sell this information, this 3D models of the cities for computer games and movies in Hollywood, because then they do the CGI, when the cities get destroyed by meteors and stuff like that. So they get a lot of money from that. They don't get a lot of money, for risk reduction. So that was a little bit disappointing that they were not planning to collect that information. But what do we do when we need to do this for entire countries? And I will show you that GEM has built this global exposure model for entire countries, for the entire world. What we do is we collect a lot of information from the housing census. Okay, you can almost imagine, the housing census and the socioeconomic data like the earthquake catalogs, which are used for the seismic hazard models. We use a lot of satellite data, in particular for countries that local data might not be reliable, like, for example, from Haiti. We do a lot of online surveys. Okay, we send these Google surveys to different experts in different parts of the world. Okay, And then we do a lot of workshops. Okay, we go to the different countries, we present the models. This is in Colombia, in Medellin. Okay, this is in Chile, in Santiago. I think this is in Peru, maybe, and or maybe here. But basically, we go there and we do this workshops where we ask people, how are your buildings? We share the data. They give us data. We criticize the model. We open the model and we improve the model. So this is something that is very important. And here I'm only showing, these are just the places in different parts of the world where we did these workshops, okay? Where we flew people from different countries, we met, we open the model, we look at the model, we see what was useful or not useful. In here, I'm almost done with the exposure part, but I just want to show you what is the outcome of this exposure modeling. This is, for example, the model for Costa Rica. What do we have? So for the different administrative divisions, we have the number of buildings, okay, commercial, industrial, and residential. We have the main construction material. This is confined masonry, reinforced masonry, reinforced concrete precast, wooden, other materials. Sometimes we can also have adobe if we go to different parts of the world, okay, the main construction materials. The distribution of the costs between residential, industrial, and commercial, okay, the number of people. Sometimes we also have population divided by gender, by income, by age, and this is all information that we need to include in the model in order to estimate the impact from earthquakes. Okay, we did this for all the countries in the world. This was an effort that took many, many years. And then if I spatially disaggregate the number of buildings, I get this. Okay, so before I showed you a global hazard map, right? That was the one that was produced by my or the effort that was led by my colleague Marco. And we had like global seismic hazard at the global scale. Now this is the number of buildings, okay, also in an evenly spaced grid. And if now I just overlap exposure with seismic hazard, it can give you very interesting results, okay? I'm just showing here this part of Indonesia. The height of this polygon, it's the number of buildings, okay? And the color of the polygon is the level of seismic hazard. So if you have warmer colors like yellow, orange, or red, it means that the seismic hazard is high, okay? And then blues and whites, it's the seismic hazard is not that high, okay? This is just a view of overlapping this global exposure model with the seismic hazard. We can see over there New Zealand, very high seismic hazard, Papua New Guinea, some of the Pacific Islands, the Philippines, of course, Japan over there. Look, this is massive exposure here in Japan. This is the Tokyo area, okay? Then we have here the Himalayan belt, right? That goes all the way to Iran, to Pakistan, very high seismic hazard. We have the major cities in India. Some of them don't have that much seismic hazard, that's true. But then we have, you know, Bombay and a few New Delhi that is relatively close to some places with high seismic hazard, okay? I also just want to show this process for all the way from South America to North America. We have over there Santiago in Chile, Lima, okay, Bogota, Quito. Quito also has very high seismic hazard and high exposure. Central America, you know, relatively small countries, but most of all the countries in Central America are exposed to relatively high seismic hazard, like El Salvador, Costa Rica, okay, and then all the way to Alaska. I just want to come back to this guy here. Let me see if I can do this. Before we jump into, we're still going to talk just a little bit about future exposure, but just to say that right now, I'm basically putting Nepal and Indonesia on the same level of Japan, right? I'm only showing number of buildings and seismic hazard, right? But now you could tell me, well, I think the buildings are a little bit better in Japan than, for example, in Nepal. Okay, that's true. Okay, so the difference between the results that I'm showing you here for Japan and, for example, Nepal is the vulnerability. We're not talking about the vulnerability yet. Okay, we will in a second, but that's something that is extremely important. Now, something that I also want you to take into account is that exposure is not static. Okay. Hazard models have the luxury to say that, I mean, there's obviously time-dependent seismic hazard, of course, but for very long periods of time, you know, a lot of the seismic hazard models are time-independent. The exposure can be very frustrating because you develop an exposure model, and after 5 years, that exposure is going to be obsolete, okay? Sometimes you start using data that was already gathered 2 years ago, and then you finish your project after 3 years, and you show results that are 5 years old, okay? And in a lot of the places, let me just show you this video again. In a lot of places, the cities just expand extremely rapidly. Okay, this is a time lapse from Google for some of the cities around the world, but the cities just expand extremely rapidly. So sometimes using risk analysis with exposure information that is 10 years old can be extremely dangerous. You know, maybe there's already buildings and population and infrastructure in places that didn't exist, 10 years ago. And this is something that we've been investigating quite a lot. Let me show you, for example, how much the population is expected to increase for some parts around the world. Sub-Saharan Africa, Central and Southern Asia, okay, it's still expected to increase quite a bit. So in a lot of the places, population is expected to increase. The continent that is expected to have the most population in the coming years is actually Africa. And we did a lot of analysis for Africa because of this region, okay? On this column, we have the number of buildings for 2020, okay? And we can see here that for 2035 and 2050, the number of buildings, for example, in Nigeria is expected to duplicate. So imagine if you go right now to Nigeria and you count the buildings and you get to the conclusion, there's 43 million buildings here. That's a lot of buildings. Well, I can tell that in the next 30 years, everything that you see in Nigeria is going to be rebuilt again. Okay? So you're going to have twice the buildings in Nigeria, almost twice in Ethiopia. Egypt, Congo is also increasing quite a bit. South Africa, not so much. And Tanzania is also popping up here. And then if you think about economic value, building value, because obviously if there's an earthquake, it's necessary, we need funds for the reconstruction. We also see that Nigeria is also increasing quite a bit. And we have some countries like Tanzania that is creeping in on the top 5. I will not spend that much time in Europe, but just to say that a lot of people tell me, well, the population is not increasing in Europe. Well, that's not entirely true. Again, remember about immigration. But look at the crisis in terms of the housing sector. I mean, you guys are students. I think maybe you had to move to another country. At least some of you have to move to another country. It was probably not easy to find accommodation, right? I mean, it's extremely expensive. There's not a lot of accommodation, right? So there's still a massive pressure to have more housing options, right? We have immigration, we have different pressure points, like for example tourism. We have the fact that the industry is increasing in a lot of these countries. Tesla built this factory in Germany, so there's a lot of more industrial buildings. And then if Tesla builds this factory in Berlin, there's all these other industries that are expected also to expand, because now there's this massive hub of industry here. So it's not just population increase that causes more buildings, okay? And what you see here in light gray is how much more built-up area is expected in a lot of the European countries for the next years, okay? We can see that there's still, probably not as much as in places like in Southeast Asia or Africa or Central America, but still we do expect like a lot of the building stock to increase in in Europe. So for us to take this into account when we're doing earthquake risk analysis, what we did was to look at satellite images, okay, from the past. I will not spend a lot of time on this part, but just to say that we use a lot of satellite images from 1974 all the way to 2014. This is for a place in Costa Rica, Cartago. This place was destroyed by an earthquake in 1914. And we can see the red is what existed in 1974. And then the city started to expand 1990. This is the places in yellow for 2000 and then black 2014, okay? The expansion of the cities, it's not random. There are patterns why we have this expansion on the cities. And we try to understand what is driving the expansion of the cities. And we collected all these different data sets, amenities, proximity to schools, hospitals, the slow proximity to roads, to water bodies. And what we did was to train models, okay? If you look here at the top, you can see the year. We train different models, either machine learning or agents, to learn from processing all the satellite images throughout the years. This is the great metropolitan area of San Jose in Costa Rica, okay? And the model is learning how the city expanded throughout the years in the last 40 years, okay? If we learn how the city has been expanding in the last 40 years, then I can do some extrapolations, okay? I learned from the past, and this is, for example, for the Dominican Republic. What do I expect to happen in the next years, okay? Look at the year here at the bottom, okay? The years are increasing, okay? We're going to start again, 15, 20, 25, 30, okay? And we see here how the cities are expanding. And then what you can do is, okay, let me now calculate the risk, not just for today, but also the risk for the future, in 2020, 25, okay, 30, 2050. The reason we did this exercise for the Dominican Republic is an extremely interesting country. There's significant seismic hazard. There's very interesting faults. You can see from the relief right here. If you see from the topography, there's very interesting faults going in this direction, this direction, this direction, also relatively close to the capital. And the population growth is quite high in Dominican Republic. It's one of the highest in the world. So unfortunately, earthquake risk is expected to increase quite a lot in this country in the next years.
So, Vitor, a quick question.
Yeah.
So your model, is that just an extrapolation, or is it based on some input, specific inputs, like, that you, I don't know, that you...
Yeah.
I don't know, is it just a pure extrapolation from the past, and you just basically try to have a model that is trained on what happened before? Or can you say a little bit more on the model?
Certainly, yeah. Probably I didn't put enough details on this part because I just assume the audience would like to hear just about epicenters and faults, But I'm glad that you're asking about that. So basically, what we do in these models is the exposure is being predicted. Okay, so basically we are estimating how many buildings exist today in the Dominican Republic and how many buildings do I expect to have in 2025, 2030, 2035, how many more buildings do I expect? Is it another 1 million buildings? Okay. Now, where do I expect that 1 million buildings? Okay. You can see that I'm not going to distribute the buildings randomly in the territory of Dominican Republic. There are patterns. We expect the buildings to be close to urbanized areas, close to roads, close to places where the socioeconomic conditions are ideal. Right. Otherwise, if the conditions are not there, then people don't settle in those areas. So we just predicted exposure models for the future for 2030, 35, and 40. And then I grab my seismic hazard model, my exposure model, my vulnerability, which I will talk in a second, and I calculated earthquake risk for 2035, 2040, 2045, 2050. Okay. So instead of calculating risk just for the exposure that exists today, I use the exposure that I'm expecting to exist in the future.
And the question was more, what the form of the extrapolation is. That like a very simple polynomial fit to the existing data, and it just
no, it's definitely not.
It's more involved. I guess it is more involved, but then
it's so we use two things. First we use multiple agents systems, okay, and this multiple agent systems is basically just an agent that goes into the different part of the model and decides if it wants to settle in this location or not, based on specific conditions, like I was mentioning. If it's close to an urban area, close to a road. So we use those agent systems. They're very good, for example, in predicting the behavior of people. For example, if a tsunami happens, what are people expected to do? For this part, we were not in love with that model. So we took a step back, and actually now we're using random forests. Okay, so we're using machine learning now to predict how the exposure is expected to change in the future. So it's a machine learning model.
Okay. So it's just an extrapolation. It's more complicated than a polynomial fit, but more or less it's a random forest fit.
Yeah. We also did the polynomial stuff as well. Okay, so that was the first thing that we did, was just let's just see if there's like a good curve that can fit this, but there wasn't. We had to go to more complex models.
Thank you.
So I'm cautious about the time, so I'm just going to talk a little bit, quicker now, just about the vulnerability. It's like this missing piece between the buildings and the seismic hazard. For example, we can see here, look, this is an image from the central earthquake that happened in Italy. We can see that this building here, it's more or less intact, but then we have all these buildings that unfortunately collapse. This is a very representation of what vulnerability is. These buildings were very vulnerable. This one is not as vulnerable as the other ones. So the questions we're trying to address is, what is the expected damage, the expected fatalities, expected loss, and maybe we might even have business interruption. You could almost draw like a parallel between vulnerability functions, which is what I'm going to talk here, and ground motion models. Ground motion models convert magnitude and distance and site conditions into ground shaking. Okay, and then the vulnerability model is going to convert one intensity measure level or many, okay, it could be also vector-based, but it's going to convert the ground shaking intensity measures into a loss ratios, okay? One gives you IMs, the other one gives you loss ratios or probability of damage, okay? So what we're trying to understand is, initially I have a building, no damage because my seismic intensity is very low. Then we have slight damage, extensive damage, and finally I have collapse, okay? So if I convert this into a function, into a fragility function, this is more or less what I have, okay? When the ground shaking is very low, my probability of having, for example, slight damage is very low, and probability of collapse is even lower. As my peak ground acceleration is increasing, it could be many IMs, okay, guys? It could be spectral acceleration, peak ground velocity, peak ground acceleration, average SA, could be many intensity measures, okay? I don't want you to think that vulnerability is this simplistic. I'm just using PGA for the sake of convenience. But for example, for a level of ground shaking like 0.5, there's a probability of maybe 50% that my building is going to collapse, but there's almost 100% probability that it's going to have at least slight damage. And these are the functions that we use to convert the ground shaking that comes from ground motion models into probabilities of damage, to allocate buildings into different damage states. There's many ways of developing these vulnerability models, okay? It could be local expert opinions. This was something that was done more in the 60s and the 70s because the numerical models were terrible and there was not a lot of empirical data, okay, that was being collected. So a lot of times, you know, people just get very wise people in the room. They would ask them specific questions about building vulnerability, and based on that input, vulnerability functions would be drawn. Then some empirical functions start to be developed, again, very much like ground motion models are developed, okay? And then we also have the advent of supercomputers and advanced numerical modeling, and now we can actually model the behavior of the buildings, okay? And again, you can also draw parallel with ground motion models, okay? Using physics-based to generate ground motion records, or for example, stochastic simulations, okay? So synthetic records could be compared to these analytical methodologies. With empirical stuff, it's relatively simple. Basically, we just send people in different parts that were affected by an earthquake. We check how much was the ground shaking. Okay, for example, look in this location, very close to the epicenter, where the ground shaking was high. There was a huge number of buildings that collapsed. Okay, if I get to a location that is further away from the earthquake, so lower ground shaking, I have a lot of buildings that had like no damage or only slight damage. Okay, if I plot the number of buildings expected to have to exceed a given level of damage. I think this was actually for slight damage, what I'm showing here, okay? For slight damage, I can draw a curve, okay? A log normal cumulative distribution, for example, and this is now my curve. That for a given level of PGA, for example, 0.5, I can see there's a almost 90% chance that my building is going to have slight damage. Okay. This is for empirical curves. If I don't have my data, I mean, for example, I'm from Portugal. The last time that we had a very destructive event was in 1909, okay, more than 100 years ago. So I don't have empirical data, but I can basically create models. Okay, again, apologies, the video is terrible, but I can create these 3D models of my buildings, or even more simplified. It can be just 1D models, and I can basically run dynamic analysis. I can grab those ground motion records, I apply at the base of the building, I see how the building is deforming, and I can try to understand for different levels of ground shaking, when is my building starts having slight damage, collapse, complete damage, and so on. Okay, this is just an example. If one of the advantages of having analytical models is that then I can have vulnerability functions for all my building classes, right? This is, for example, the vulnerability model that was developed for different building classes in Costa Rica, okay? I can cover all the building types. I also wanted to mention just very quickly that the seismic vulnerability of the buildings is also increasing. It is increasing as we speak, you know, for different regions. There's a accumulation of damage due to natural hazards. Like, for example, I remember that there was a cyclone before one of the earthquakes that happened in 80, okay? So a lot of the buildings were already, let's say, a little bit weaker because of the cyclone, and then the earthquake happened and destroyed like a lot of the buildings. Some buildings are not maintained. You know, this was in Coimbra, in a city in Portugal. And a lot of times, I'm not proud to say this, but it's very common in Portugal, like every 2 or 3 years, to hear on the news, one building collapsed. And there was no earthquake. You know, the building is just not well maintained, and the building just collapsed because it's not well maintained. Now imagine if there was an earthquake, even if small, it would probably cause the collapse of all these buildings that are you know, so fragile. There's this unregulated modifications. Okay, this is also in the same city, Coimbra. If you look at this store, you can see that they used to have columns here, okay, here and here, but they decided, well, I need a store for, I need a shop for shoes. So they just removed the columns here because they just assumed that those columns were doing nothing there, you know. This is also something that existed. It might be a little bit complicated for you to understand what's going on here, but this is an iron, this is a steel bar. Okay, this is a beam that is here, and they basically just cut the beam because they needed to put this pipe. Okay, but the beam exists there for a reason. You know, the beam is a structural element that is basically supporting the house, and they decided to cut the beam just to put this pipe because they wanted to put a bathroom on this other side of the house. This is extremely concerning. Okay, this is also some photos that I took some time ago in Nepal before the earthquake. You can see that this building was built in different times, right? We have something here, then we have this increment, and then there's this increment over there, okay? Here and here. This house here, if I remember correctly, this was basically a family, and the family owned a building. I think he had maybe 4 stories or something like that. And then the father died, and he left the building to 2 of his sons, okay? And the 2 sons decided that half of the building belonged to one son, the other half of the building belonged to the other son. And one of the sons wanted to build a new building. So he completely cut the building, okay? 50% of the building was gone, and then he decided to build a new building next to it. But obviously this introduced a lot of deficiencies on the building, on half of the building that remained there. So just to see, and a lot of times this happens because the family increases, and basically they just want to add more stories and more stories and more stories to maximize, you know, the houses. But this is very concerning because a lot of this part of the structure was not designed to have, you know, 6 stories. Sometimes it was designed just to have 3 stories, like what you see here. Okay, so this is what happens. You have 1 story. Let's put a little bit more building here, more and more, and then the vulnerability, you know, starts to increase. Okay. There's also some issues that I just want to mention, which is related with, you know, aging effects, okay? If you go to Pavia downtown, you will see there's a lot of old buildings, more than 500 years, some of those buildings. Obviously, the structural capacity of those buildings that exist downtown in Pavia, it's not the same that it used to be, you know, 500 years ago. And this is also something that needs to be taken into account, okay? Yes, I'm going a little bit quicker because I think I have 1 minute and 30 seconds. But just to say that we estimated how much the risk was expected to increase in Montenegro just because of aging effects, and in some places it's quite a lot. I'll just skip some part here. Yes, I just wanted to mention that, as I mentioned previously, liquefaction hazard is also expected to increase. There's many publications about that. This was just a landslide that existed in Indonesia some time ago. It was a massive landslide, and unfortunately, I think it killed a lot of people in Palu, in Indonesia. I think 1,200 people. So when the earthquake happened in Zagreb, sorry, in Croatia, I went there and I asked my colleagues to take me to some specific places in Petrinja, because I look on the map. When I was on the plane, I look on the map and I saw, oh, you know, very close to the epicenter, there was a creek. Okay, and I also noticed that from the digital elevation model, there was some interesting slopes, you know, close to the creek. So I thought maybe there was some liquefaction there. My colleague first told me, I don't think there was any liquefaction, you know, on that event. I was like, okay, that's fine, but let's go there. And then we noticed that there was, you know, a little bit of liquefaction on the on these parts here. You can see here. And then we actually talked to the people. My photo here is not great, but these 2 houses, they basically came together at the top. You know, they were tilted a little bit because of some problems of vertical settlement due to liquefaction. And the owner of this house, it was this guy actually built houses. That's what he did. You know, he built houses. And it was initially telling me that he was so proud when he built his house, when he built this part of the house, there was like this slope. So every time that it rained, the water would go in this direction. And now, because of the earthquake, the slope is the other way around. You know, the house settled because of the earthquake. So now the water goes against his house. And he was telling me that he was quite sad about that, because he was like, I actually thought about this when I built my house, and now because of the earthquake, I don't have this part. But again, just to say that the reason why this earthquake, there was liquefaction here, was because the water level was relatively high. If we have sea level rise, the water level might increase even more. Okay, we develop a machine learning model, again, to predict that. I'm just going very quickly, just to say that we actually evaluated in different parts in the Balkans what is the type of earthquakes that can generate liquefaction in parts that are not a concern today. Okay, this is the impact for 2020, but will become a concern in 2050 just because of sea level rise. Okay, we check how much the water table is expected to increase in these places in Montenegro and Albania. Albania is here in the south. And what you see here in black is the places where there's a high likelihood of having liquefaction in 2050 if the same Montenegro event of magnitude 6.9 happens. So I just wanted to finish with an actual example of putting all these pieces together. Okay, so I have my seismic hazard model for Turkey. I have my projections of the population for the future. I have my vulnerability functions, okay, for all the different building classes. And I wanted to give you an actual example of the data, this project that was done, given to the World Bank, and then the World Bank is giving 750 million, not giving, the World Bank doesn't give anything, is giving this loan, okay, to Turkey to improve the resilience of the building stock, okay? So we started by calculating the risk today. This is the average annual economic losses on the different provinces of Turkey. Turkey is an extremely interesting country, okay? We can see here that actually the earthquake risk was not that high in the places that were affected by the earthquake. But this is, I think, a very good, lesson for us, because just because the risk, is not that high, it doesn't mean that you cannot have this, very rare earthquakes that happen in specific parts. Okay, this is a war that I have in Portugal all the time, because the risk is not that high, but it doesn't mean that another 1755 earthquake might not happen. Then initially, what we give to the World Bank was just the base calculations. Guys, this is the average annual economic losses today, 2030, 2040, and 2050, okay? We had a meeting with the World Bank, and the World Bank told us, okay, that's okay. But now I want to understand, what if I could magically, okay, I'm going to magically retrofit all the buildings before 2000 and also after 2000, okay? If you do that, if you retrofit all the buildings before 2000, this is how much the risk is going to decrease. If you retrofit all the buildings after 2000, this is how much is going to decrease. Okay, but this is magic. We cannot retrofit all the buildings in Turkey, at once. So then the World Bank told us, okay, now what if I do nothing for the buildings that were built, before 2020? But all my new buildings for the future, now I'm always going to build according to the best design regulation that exists in Turkey. So this is what happens, because we're still adding more buildings, the losses might be lower, but the risk is still increasing because there's still more buildings. And even if the buildings were designed according to the best design regulation in Turkey, the losses are not zero, okay? This is something that also people need to understand. Just because you're building according to design regulation, it doesn't mean that the losses will be zero. It just means that the losses will be lower. The building is not going to collapse, but it might have slight damage or moderate damage. So when we presented these results to the World Bank was not happy. They said, well, I cannot go to the country and say, I'm going to give you, this amount of funds, and you're still going to have the increase in your earthquake risk. So then they told us, okay, we need to retrofit. And this is exactly what they're doing there now, more in Istanbul, not for the rest of the country. But what if I retrofit some percentages of the buildings built before?
The very last minute is gone.
Yeah.
It's starting to decrease, okay? And then finally, in 2050, it decreases quite a bit. Okay, so we need to follow design regulations, but we also have to gradually, okay, even if very slowly, we need to start retrofitting some of the buildings. Okay, so this is it. And apologies for going 5 minutes over the time, but I just want you to have like a good, end-to-end overview from the seismic hazard to the exposure to the vulnerability to running risk calculations. And I just wanted to give you an example of how basically the different pieces can come together for risk reduction. And happy to answer any questions in the time that we don't have.
Excellent, Vitor. Thanks a lot. That was a very clear, very stimulating lecture. Well, I learned a lot myself, but I'm sure the students did as well. Guys, do you have any questions for Vitor? Please go ahead.
Maybe I have a question.
Go ahead, Aurora.
Oh, it might be silly, so please correct me if I say anything wrong. It is a question that came to my mind when you were talking about exposure and exposure models in particular. I was wondering how much the detail in constructing an exposure model can affect the vulnerability assessment. I mean, is it something that can be quantified? Because I guess that modeling exposure with much detail is something that can be expensive in terms of time and money. So I was wondering if if it is something that can be estimated. I mean, is there like a level of detail after which the vulnerability assessment doesn't change much?
Yeah, very good, Aurora. It's not silly at all. It's a very interesting question. So I can tell you that, for example, in some of the risk analysis that we did in 2014, okay, 10 years ago, some of the exposure models we were developing, they were super rough. You know, I'm even embarrassed of saying, but for some of the countries, there was like 5 or 6 building classes. You know, we were saying, I think it was for Japan, if I'm not mistaken, we're saying, let's do one vulnerability function for wood, one for concrete, you know, one for masonry, but it was very simplistic, right? And then we keep improving the models, and now there's more building classes. We put more detail, more detail, more detail. And the vulnerability needs to match this level of detail, okay? It's a little bit silly that I have, for example, 100 different building classes in my exposure model, and then I have 10 vulnerability functions on the other side, right? So we always have to be careful that if you create, with great power comes great responsibility. If you create like a very detailed exposure model, you also need to have a detailed vulnerability model, and that can become extremely expensive as well, okay? I will also say that also something that you picked up that is very interesting, which is it worth for me sometimes to continue improving the exposure? You know, it needs to saturate, you know, eventually it saturates. And it does. I can tell you that if I'm going to do something very detailed for a specific city, yes, maybe it's worth for us to go into, you know, more detailed exposure. But for example, in the project that I was showing you, we were doing things for Turkey. Okay, I don't need a building by building, you know, exposure model or something extremely detailed if I'm doing things at the national level, right? At the national level. So I think it also depends a lot on the purpose of the project. If it's at the national level, maybe you don't need that expensive, you know, complex exposure models. Once we start going to urban level, we do need to invest a little bit more and adding more detail to the model. Thank you, Aurora.
Thank you.
I had maybe a similar question, just from when you were describing the two different approaches when considering the seismic hazard, that you prefer the probabilistic approach where you consider everything. So then my question comes in, how do you know that you've considered everything in the same way that, how do you know you're not leaving out something that might be really important? How do you find that limit?
No, typically I blame the Ezra modelers, okay, if I'm missing something, okay? So when I say, yeah, very good question. So when I say that I prefer to consider all the possible events, granted that all the possible events that might happen have been considered inside of the PSHA model, okay? I can tell you that for the earthquake that happened in Japan, okay? So GEM, when earthquakes that are labeled as red by Pager, we need to calculate the impact of those earthquakes in the 3 days, 5 days after the earthquake happened. So I was the one in charge of January, so I had to calculate for Japan and also for China. For the Japanese earthquake, my colleague Marco contacted our colleagues in Japan right away, and we noticed that on the PSHA model, on the seismic hazard model that we have for Japan, the seismogenic source that exists on this part, it doesn't contain events of magnitude 7.5. Okay, I think the maximum was like 6.9 or something like that. And then if you go a little bit towards the east, then the PSHA, the source model for Japan, can generate magnitude 7.5s. But at the location of this event, the model was not capturing that event. Okay, so that means that, going back to your question, Rachel, if I was going to use the PSHA model for Japan, I would be saying, oh, I'm considering all the possible events. That's not true, because we just noticed one event that was not there. But I still think, yes, there will always be limitations in PSHA models. We know that. That's why we have more research on the location of faults, geodetic, information. But I still think it is better than just to consider like a couple of scenarios. Okay, in my country, in Portugal, the authorities consider just 2 events, to do all the civil protection stuff, the preparation plans. It's a magnitude 8.5 offshore in the Atlantic, and the magnitude close to 6.0 in the Tagus River, and that's it. And I think there's many other events that should be considered when building this risk mitigation plans.
Thank you.
Thank you, Rachel.
I have a question regarding the secondary effects like liquefaction, because the one landslide you showed was, of course, very devastating. But then on the other side, you mentioned the Petrinja earthquake, and I've been there, so I know that Petrinja, the region, most of it is quite flat. And I've seen the sand blows and the cracks produced by the earthquake. But also I've seen the entire city center was completely collapsed. So sort of the magnitude, the importance of these secondary effects for actual building damage, for actual hazard, I think they probably depend a lot on other circumstances on the region. So how do you deal with that? How do you account for that?
I mean, for example, we saw that in Christchurch, I think the vast majority of the damage was because of liquefaction, right? Not because of the ground shaking. And I was already, so this, are you from Croatia, if I can ask you, Alexander?
No, I'm from Germany, but I was in
Germany,
Croatia to help out in the field.
Okay, I was only asking because when we went to visit this part here, I asked what was the name of this place we were visiting. I don't remember the name now, but the name in Croatian is clay. If you translate, it's clay, so it's soft soils. And I asked my colleague, oh, clay, what do you mean? So it's soft soils in this part. And it was like, exactly. So there's a lot of clay. In fact, they had, I think, a mine or something like that in this particular part. So I think in some parts of the world, considering liquefaction and landslides, should almost be like mandatory, because there's not a lot of damage, due to the ground shaking. This is also the case, for example, in some parts of the world where the buildings are quite resistant. Again, New Zealand. So I think the ground shaking alone wouldn't be sufficient to cause like this level of damage, but then the secondary hazards can cause that level of damage. This is extremely problematic for somebody like me, that I have to estimate the impact due to earthquakes, because how many ground motion models do we have? Hundreds, right? We have hundreds of ground motion models. Some of them are updates from past ground motion models. Of course, I understand that, and I'm really glad, every time that we have some improvements on a lot of these ground motion models. But then if you look at the counterpart on the liquefaction, now I would ask you, what about how many models do we have to predict, for example, liquefaction? There's no comparison. I can count with the fingers of my hand, how many models we have to predict liquefaction or landslides. So I think it's a field that is not as mature. Okay, there's models from the USGS. Okay, the Pager system, they apply some models, probabilistic models, just to highlight the areas where we expect like liquefaction. But this is like a yes or no model. I need permanent ground deformation then to estimate the damage in my buildings, and this is something that it's still not there. So I don't have a good answer, Alexander, for you. I can tell you that we've been exploring some of the existing models. I think we're doing relatively good when it comes to estimating damage due to ground shaking. We're not doing good enough yet for the secondary hazards.
Okay, thank you.
Thank you. Laura, I think.
Vitor, should I add a piece of information in the super nice picture you did? Well, and this is valid also for the question raised by the students. Usually, seismic hazard models are simplified images of the reality. And usually a seismic hazard map does not consider local site response effect. So before talking about secondary effect, we have to be sure that the ground motion predicted by our model is really adequate to the local site conditions. The map that are produced for regulation are given in the simplification that the earth is flat and the terrain is rigid, and you have to apply some, let's say, additional component of the ground motion to model the local response. So the destruction inside a city, for example, are surely due to the different vulnerability of buildings, but most of the times are due to a different local response that is below the, let's say, last 20 meters of soil below the building. So this goes also in the direction of saying that if we do not improve simultaneously our knowledge about the local site condition and the knowledge of the vulnerability, we will never have a realistic model of the real damage that we can expect. And this is something that has to be taken into consideration, even if, of course, we accept simplification, because otherwise we cannot give a rough estimate of the mechanism and of the phenomenon. I hope this comment goes in the direction of making some stuff more clear.
Yeah, very much, Laura. So thank you very much for that. And in fact, the Julian, who's also here on the call, this is something that worries me a lot, because a lot of the PSHA models, they provide, ground shaking typically on rock, but then the ground shaking on rock or on bedrock is not very useful for me, because I don't have my buildings on bedrock. I have my buildings on the surface. So something that, for example, Julian is doing is exactly testing like all these different, methodologies to take into account, site response, from global VF30 to local measurements to nonlinear amplification to all these different methods to understand. I mean, these global methods, these simplified methods are never going to be perfect, but in a lot of places around the world, there's nothing else that we can use, unfortunately. But let's try to quantify the uncertainty and the bias and be a little bit more informed, So when I'm showing like some of these risk results, I can say, well, yeah, this is a simplified picture, as Lara was mentioning. And by the way, this is all the uncertainties and the bias that we can expect for some of these estimates. Very good. Any other questions?
Apparently not.
Yeah.
Okay. Well, Vitor, thanks a lot again for your.
Thank you, David. Thank you.
That was very clear. Very good.
Okay.
Vitor, should I ask you to remain in the call for just a couple of minutes after? Because
yes, of course, Lara.
Okay, thank you very much.
All right, so we can I'll stop the recording and we can stop for tonight. So Laura, you want to?
I just would like to talk, let's say, privately with Vitor for organizing the training school.
So don't